class. Now I am concentrating energy of a capacitor. So in a capacitor, that is a charged capacitor, how much energy is stored? Because capacitor is an energy storage device. This energy is stored in electric field form. But how much energy is stored? That is our present question. How much energy is stored in a charged capacitor? Okay, just wait. Now I am taking one parallel plate capacitor. Parallel plate capacitor separated by the distance d, that is two plates separated by the distance d. Two plates having same surface area, that is A, and medium is a free space, that means capacitance is a epsilon naught by d. So plate number A having plus Q charge, plate number B is having minus Q charge. So that parallel plate capacitor already charged. Yes, how much absolute charge? That is a Q. One plate is a plus Q, another plate is a minus Q. Absolute charge stored is a Q. And in between these two, electric field E equal to Q divided by A epsilon naught. That electric field is a uniform, and nearer to edges some small non-uniformity is there, that is a fringing effect, but that is excluded, neglected. So electric field Q by A epsilon naught is a uniform electric field. That is only between A and B only there. Here and here electric field so 0. Here, by using three different methods, I am finding energy of a parallel plate capacitor. So first method I am using the concept of electromagnetic wave. The energy density related to electric field, that is half into epsilon naught into electric field square. That means wherever electric field is there, there is a storage of energy in the form of potential energy. That energy density, energy per unit value, energy density is half into epsilon naught into E square. That is electric field square. But here electric field is Q by A epsilon naught. So that's why students, here I am writing half into epsilon naught into Q divided by A epsilon naught whole square. This is energy per just unit value. But volume of our capacitor A into D means in that value energy is being stored. So therefore total stored energy is half into epsilon naught into Q square divided by A square into epsilon naught square into A into D. Because here electric field is a uniform, that's why direct multiplication. Suppose electric field is non-uniform, integration mandatory. So after small simplification, Q square divided by 2A epsilon naught divided by D. But students, A epsilon naught by D is nothing but a capacitance of capacitor. So therefore, Q square divided by 2C is nothing but a energy stored in that particular capacitor. Q square by 2C. Q is the absolute charge stored in a capacitor of capacitance to C. So energy stored is a Q square by 2C. This is the method one. I am now using another method also, students, just wait. Here, two parallel plates. One is plus Q charge, another is minus Q charge. So definitely there will be electrostatic attraction between these two plates. That force also we know, Q square divided by 2A epsilon naught, the previous class completed. So due to that electrostatic attractive force, these two plates are getting attracted. To overcome that, some external agent or some external force is required to overcome that. So this external force in separating these two plates from almost zero distance to small d distance, some work has to do. This work is against electrostatic force. That means whatever may be the work we are doing, that is external agent doing, that is stored as a potential energy. That is the second method now I am using. So here potential energy equal to electrostatic force, that is Q square divided by 2A epsilon naught force into displacement, that is from zero distance to d distance. Right now d distance to maintain. So force into displacement, that is now stored as a potential energy. Yes, Q square by 2A epsilon naught into d. Yes, again A epsilon naught by d is a capacitance. So that's why Q square by 2C. This is the second method now I used. Now I am going to find the same thing from third method. See students, third method, originally capacitor is not charged. Capacitor is neutral. Plate A and plate B have no any charges. Now, by using some external agent, we are charging the capacitor, that is by giving charge plus Q to plate number A minus Q to plate number B. But we can't give total charge capital Q at a time to the capacitor. So slowly we need to give charge to the capacitor. Suppose zero charge to 10 microcoulombs, all of a sudden now capacitor can't be charged. It takes some time. So that's why now first I am taking capacitor. At any one instant, this is plus Q, it is minus Q. That's why potential V equal to small q by C. At that time, potential is a small q by C. Therefore, in further charging small dq, whatever may be now work we are doing stored as energy. So that is du equal to V into dq. That is V is nothing but a q by C into dq. So this is the extra energy stored in charging of a capacitor through small charge dq, q by C into dq. Now total charge stored, how much potential energy? U equal to integral q dq divided by C. That different integration we know 0 to capital Q limitations, because final charge is capital Q. Q dq is a q square by 2. So therefore final answer q square by 2. So q square by 2c, q square by 2c, q square by 2c. Whatever may be the method now you are using, final stored potential energy in a charged capacitor of capacitance C, Q square by 2C. Q is the total charge stored in that capacitor. C is capacitance of a capacitor.